All right. Hello, 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 everybody. Hello, hello, hello. Hello, everyone. Guess we'll wait a few more minutes here. We'll have people come in and such. But nonetheless, hello. Hope everybody's doing okay. Notifications out of my way. Right. We'll wait a few more minutes here. Should be good to go. Okay. All right, right. We will wait some more time. That's what I gotta do. Okay. Alrighty. See if I've usually start off late. Hopefully we can get started soon. Some people showing up. I see you're there, Anna. I I couldn't tell you. I couldn't tell you, Anna, if everybody's hibernating or not. I have no idea. All I know is I gotta do a lesson here eventually. But if you know, maybe everybody's in a food coma. Maybe it's lasted a whole week. I have no idea. I'll probably just start whenever the first person comes in. So I'm not sure. Well, they'll have to come at their own time. Fernando! Hey, buddy. How are you, my friend? Sure. What homework do you need help with, my dude? Section 12.1? All right. Go ahead and tell me what the question is. Number 10? All right, let's take a gander at that. I got your assignments right here, so. Oh, you know, helpful if I just go there. Helpful if I just go to the assignment, for goodness sakes. Yeah. Hey. All right, let's take a look here. Okay. So you need help with the frequency chart, right? So all you need to do here, Fernando, is you just need to take a look here and see, like it says hours studied 15, right? So you just need to count how many data items are labeled 15, and that's going to be your frequency. So if we look at the list carefully here, I see 1, 2, 3, 4, 5. Remember, frequency just represents how many times that data item appears in the data set. So I would say 5. And then I'd be like, yeah, because I'm amazing. So, not really. So 16. 1, 1, 2. Let's see, 2 16s. How many 17s? 1, 2, 3. Let's see, 18s. 1, 2, 3. 19s. 1, 2, 3. Like 3 19s. 20s. All right. So one thing to keep in mind here, Fernando, is that even though I don't see any 20s, I'm still going to represent that. I'm going to represent it with 0. Okay, so that's still okay. All right. And then you just keep going down the list, okay? Until you have a full frequency distribution for all the numbers. Looks like up to 25 looks to be your highest amount there. And that's all you got to do for that problem. I promise. Nothing more to it than just that. Do you have any questions about that? Yeah, we got some people to come in. Hey, no problem. I'm here to help, my man. You gonna stick around today? Got some good juicy math to do, you know? All right. Oh, today's your last time being on the stream? Why is that? Why is Oh, okay. Okay. No, that's fine. Like you do you, man. I got nothing against that. You do you. That's perfectly fine. I understand all have livelihoods to make, so that's perfectly cool. All right. We all ready to go? Okay. Yeah, school will be over actually I'll talk about that here in just a second. All right. Let's do this. All right. Okay, let's get started today. Welcome back. Welcome back to Monday. Hopefully, you had a very wonderful Thanksgiving holiday. All right, I know I did, and yeah. In any case, let's talk about a few things on the agenda here for what's upcoming. We are now currently in the home stretch for the remainder of the semester. Okay, so of course, the last chapter here is chapter 12. All right, let's make a couple notes here. First of all, there's no final exam for this class. Chapter 12 will be the final chapter, and that'll be the effectively end of the material. I'll post a test on chapter 12. You'll get that finished, and there you go. Do the homework, and that's it. That's the end of the semester in a nutshell. Okay, so that's essentially what we're working with here so far. All right, now, um, again, the homework there will be open until the end of the semester. I expect the Chapter 12 test to also be open until probably close to the end of the semester. So that'll be fine. In any case, again, how many sections are left on Chapter 12? Well, there are, after today, we're going to do one section, and then after that is going to be two more sections, and then effectively the book will be finished. Okay, so 12.4 is what we're going to be doing here today, but we're also going to do 12.5 and 12.6. 12.5 is a relatively short-ish type of section, and 12.6 is the last section there that we'll talk about. Okay, and then that'll be it. So technically we have 4 classes left. Okay, we have today, Wednesday, and then the following week, and then the following week after that, I believe, is going to be finals week. So, uh, yeah, and so that's pretty much how it is. What it do? It do what? It do what? Question mark. All right. So I guess that's the question that we have to do. Is the grade on my math lab accurate? Yes, so far anyway. Obviously, I haven't graded everything, and the homework score is still an ongoing thing. So obviously, you can improve your score for the course by doing more homework assignments and getting as close to 100% as possible, along with doing good on the tests. Okay. Um, of course, that factors in as a grade there. So if you didn't do so hot on a test, then it's not a huge negative against you because the homework can lift you up for some of the gaps that you did miss. So the system is designed that way in that regard. Do you get credit for the practice test? Um, you don't necessarily get credit for the practice test, but I'll consider giving bonus points. So I'll make that consideration. I think that's fair to say. Any other questions? I know remote learning has been tough. I know nobody wanted this situation. I understand that. Nobody wanted this situation at all. But we've made the best of it throughout the course of this semester. So, I hope you've been able to put up with me at the very least. So, for the past, 12, 13 weeks or so. So, I just hope that you enjoyed your time here in this course. So, That's, I guess, I can only do so much, but you learn something, you got something out of the course. I'll be very happy with that. Yeah. Well, I know that there's some people who are like, you know, I I just kind of like the like the relaxed way I teach or something like that. I'm just kind of curious. That's all. I mean, yeah, I try and be chill. Look, I've been there. I know the perspective. Sometimes I gotta lay down the hammer, and sometimes, well, actually, most of the time, I gotta think from your perspective as well. So I find that to be more important. So just force feeding information through doesn't necessarily always work. I mean, I have a lot of spoons in my drawers in my kitchen, but yeah. It doesn't have to be crazy hard. Some people take some people are like super serious. I'm like, why do you have to be super serious all the time? Like, no, you don't have to be. You could just relax. Oh man. Yeah, actually, that's kind of weird. I'm not sure why that is. Take out their yeah, you know what? That's not right. If I'm angry, on a personal level, if I'm angry, I don't have a right to take that out on you. I've had that happen. Okay, great. Thank you so much, Selena. Um, no, I mean the thing is that I've been angry before, when I came home and went to school and stuff, but very rarely have I taken my anger out, and very rarely do I, you know, there's people who have bad days, but if it's all the time, then really, I think people need to rethink what they're doing. So really, when if I come to work, then it's usually I'm having a bunch of fun. So anything to goof off for like hours on a day. Yeah, it doesn't make any sense. It's just like, why are you so mad? Why are you so stressed out? I mean, shouldn't you be enjoying what you're doing, or what? Why is it have to be? Why does it have to be like all negative Nancy all the time? In some cases, I can understand. Like some teachers are just bound by red tape and politics and whatnot, and that really sucks for them. So be sympathetic. If there's one thing to be sympathetic about for teachers like that is like sometimes they want to do certain things and they can't because they're being restricted by things that they can't control, and that in itself can be very frustrating. From a teacher's perspective, they want to help you and they want to kind of go off the rails a little bit in order to do that, but they can't because they're risking their job or they risk the school's reputation or something like that. So it isn't easy. But when you're in college, and then it's like, okay, now the floodgates can open. And you can be like, all right, let's sit, chill. Let's just talk on the level. Sometimes it's just like, on one hand, there's kind of high school, and high school's all about the kid gloves. Then when you get to college, it's like, yeah, you're an adult. Let's go. So, you know, something like that's kind of important there as well. All right. Well, let's get to uh let's get to doing this stuff here. I think switch our camera here. Bam. Okay. All right. So let's go ahead and get started with today's lesson. All right. So today, what we're going to be covering here, specifically in section 12.4, is we're going to be covering the normal distribution. Okay. So we're going to be talking about the normal distribution here for today in section 12.4. Now, one of the things that we talked about here before is we talked about standard deviation. And actually, in the last section, we talked about how to find standard deviation here by hand. Okay, that's essentially what we did here. So, what we're going to be doing here today is talk about more about that standard deviation here. Only this time, we want to put it into a context in which we can understand and interpret and work with. So, how we're going to do that here is we're going to work with a couple of things. Okay. So, in order for us to understand the normal distribution here, we first need to understand what it represents. Okay. Again, it is a chart here. It looks like a bell curve. Okay. Now, if you're not sure what the bell curve does, is like if you want to create, say, if you're a teacher and you want to create a fair test back in the day used to be like, okay, you know, a few people got A's, a few more people got B's, majority of people got C's, and then the same amount of people got B's got D's, and then the same amount of people got A's got F's. That would be representative of a fair test because it would be in a bell-shaped curve like you see right here. Okay, now let me just go ahead and put out a tool here. Okay, so how does this normal distribution curve work? Well, it kind of works like this. Here we're going to have, again, let's say we have a normal distribution curve. It looks like a bell curve, looks like this. All right. Now, dead set here in the middle, we talked about a few things here last time to find out what standard deviation is. And let's say we took this graph and we chopped it in half, okay? If we chop it in half here, right here in the middle, we're going to call that the mean. All right, so the mean of a data set here is going to be kind of like your middle point. And everything around the mean here is going to reflect um, either a good standard deviation or other side standard deviation. Now, one thing that we want to look at here is that we can go a certain amount of standard deviations to the left and right. Okay, so let's talk about that right now. So on the right hand side here, let's say we go one to the right here. This line here represents the mean. I'm going to just kind of write this once here, plus one standard deviation. And I'm going to describe what that means here in just a second with a couple of examples. Maybe you go another step up here. Maybe you do plus two standard deviations. You can even go another step up here, and you can go plus three standard deviations. Okay. Now, on the other side of things, we can also go minus one standard deviation. All right, we can go minus two standard deviations. Or heck, we can even go minus three standard deviations. Okay, so this is what a normal distribution curve kind of looks like. We can you can chop that up into little categories there. You can go plus one, plus two, plus three standard deviations to the right, or minus one, minus two, minus three standard deviations to the left. Now, having said that here, let's discuss about why we can get positive or negative standard deviations. And for us here in this case, let's go ahead and do an example. All right. And let's go ahead and do a couple of examples here, and you'll see why we can get plus or minus here as part of our number of standard deviations. So I'm going to look at a specific problem here in the book, a couple of them. Okay. All right. Now, let's take a good look here at a couple of these problems, all right? So, it says the scores on a test are normally distributed with a mean of 100 and a standard deviation of 20. We're going to find the score that is, let's start off with this one here, 1.5 standard deviations above the mean. Okay, so let's talk about how we can actually find that here by hand. And it's really not too hard. All right. So the way we're going to figure this out is, let's, where do I want to put that down in here? Put it on, let's put it on a Word document, I guess. Was that oh, it's not where I want. Second, folks. All right, there we go. Okay. So the way we want to figure this out here specifically, like in an example like this, um, is basically we're going to do this here first. So let me. So notice here that we have in our example, we have number 4 here. We have 1.5 standard deviations above the mean. So the key word here is going to be above the mean. Okay. So the key words here are going to be above the mean. Yeah, wait, what did I just do? Why did I do that? Anyway, that doesn't make sense. Anywho. So what does that mean to be above the mean? Well, let's talk about it. If we want to find the data item, so the one thing about this is that we want to find the specific data item that is 1.5 standard deviations above the mean. So we're going to fall underneath one of two categories. First, above the mean. So let's say you see the word above. Then the data item that you want to find here is equal to the mean plus the number of standard deviations times the standard deviation. All right. So in our case here, for our problem that we see here in front of us, then the data item in this case, we are given here, we're given a mean of 100. Okay, so the mean is equal to 100. And our standard deviation, according to the problem here, is equal to 20. Again, these are just random numbers. They can literally be anything. But here you go. So if I want the data item here, it's pretty simple. I take my mean of 100. I add that to 1.5, so 1.5. And I multiply that by 20, being the standard deviation. I do that all out, and I'm going to end up with a data item here of 130. So 130 here reflects 1.5 standard deviations above the mean. Now the same thing applies here. Well, similar thing applies, I should say, for below the mean. Well, let's take a look at an example of that. Sorry about that. So let's look at the next one here. Try 2 standard deviations below the mean. So this is so again, our keyword here is below the mean. All right, and so again, what does below the mean mean? That means that you have the data item is equal to the mean minus the number of standard deviations times the standard deviation. All right, so in this case here, we're trying to find the data item here. So the data item here is going to be 100 minus, in this case, 2 standard deviations here. So 20 times 2. And so this is equal to 60. Okay. All right, so 60 would be the data item that would reflect 2 standard deviations below the mean. All right. Any questions about that so far? Any questions, anyone? That over. All right. No? Okay. That's perfectly fine. Not a problem. All right. Well, let's talk about the next part here. Okay, so there's a lot more to talk about standard deviations. This is just kind of like the tip of the iceberg. So let's talk about, that's just getting a data item there from a particular, how many standard deviations something is. Now, the next part that we're going to talk about here is we're going to talk about a very specific rule here, very unique to normal distributions. And that's going to be the 68, 95, 99.7 rule. Okay. Now this here is unique just to, first of all, let's make a note here. Note this is unique to normal distributions only. There are lots of different types of distributions, again, probability distributions, but this is a very unique one here to normal distributions only, so only based on the bell curve here. Now, how does it work? What exactly are we trying to say? Well, first of all, each one of the numbers that you see here reflects a percentage. But a percentage of what exactly? Well, here's how it looks. 68% of all data items in a data set are within 1 standard deviation of the mean. Now, you're probably saying, whoa, 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 time out. What exactly does that mean? Well, let's look at a picture here and let's put it on our said picture that we had made earlier. So this is our picture of the normal distribution. Okay, so this is a normal distribution, all right? With our markings on it. Now here's the contention that I'm making here in this case. So from here, I'll put this in blue. Actually, no. Right. So from here to here, this area marked in red This represents, in this case, the 68%. So this represents the 68% of data items fall within one standard deviation of the mean. What that means, again, it's between -1 standard deviation and +1 standard deviation. Okay, so 68% of all data items will fall underneath that category. Okay, that's what essentially it's saying there. We'll see exactly how that works here momentarily, but again, just giving you a heads up. All right. The next part here is 95% of all data items in a data set are within 2 standard deviations of the mean. So how do we reflect that on our picture here? Well, let's go ahead and put this in green. So from here to here in green, this represents 95% of all data items fall between -2 standard deviations +2 standard deviations. Finally, talk about 99.7%. So 99.7% of all data items in a data set are within 3 standard deviations of the mean. Okay, so again, if I mark this one more time, mark this in orange. So between here and here, this represents 99.7% of all data items in a data set. Okay, so that's essentially how that will work. Now, other things to keep in mind, something very important here, okay? Here's what's nice. Because it's a bell curve, right? That's what the normal distribution looks like. And because it's a bell curve, it's also very, very predictable. So much so that one thing that we're going to take to the bank here is that the normal distribution is symmetric about the mean. So the mean here is in the middle. And so you could have, like, say, 50% to the left and 50% to the right. It is a perfect symmetric graph. It cuts it directly in half in equal portions, and it looks exactly the same. So that's what makes it very, very convenient, because it is a predictable graph that certainly can have consequences, but easy to see consequences since it is symmetric in nature. So what does that mean here in this case? Well, it means that the percentages between each of these bars here is also predictable because of that fact. Because it's perfectly symmetrical, think of it this way. If I have, let's put it in orange again. Okay, so between -1 standard deviation, 1 standard deviation, we said that was 68%. Well, cut that in half. 68 divided by 2, and so we have 34% here and 34% over here. So if 68% of all items are between -1 and +1, well, they actually evenly split right down the middle, 34 and 34. Because again, underneath symmetry, they should be the same values. We do the next one here, and the next one here is between -2 standard deviations and +2 standard deviations. Now that's 95. However, we already have 68% already accounted for. So we just do 95 minus 68, which is set 27. Then cut that in half. That's going to be 13.5% on both sides. Next, we have between -3 standard deviations and +3 standard deviations. That's 99.7%. So we have 99.7 minus 95, so that's going to be 4.7. Then divide that by 2, we get 2.35. We get 2.35 here, and 2.35 here. Now we still have to represent the entirety of the data set, all 100%. So the last portion that we haven't accounted is the last 0.3% according to this rule here. So the last 0.3% here, or again 0.15 on both sides by cutting it in half, is what we'll get outside of 3 standard deviations to the right or left. And there we go. We have our full chart here with our percentages in each respective bar. Okay, now having this little picture here will be very, very helpful for what we want to do. Let's go ahead and talk about why. All right. So let's go with a couple of ideas here. All right, so that way it makes it a bit easier. And the one that they show you in the book is good, but I do want to show you another problem in the book here that's a little bit more relevant to see how to kind of get this stuff from scratch. So, okay, so the one I want to do here is going to be number 20. Let's do 20. Let's start off with 24. Okay, so it says IQs on the Stanford Binet scale, a Binet intelligence test, are normally distributed with a mean of 100 and a standard deviation of 16. We're going to use the rule that we just talked about here, the 68, 95, 99.7 rule, to find the percentage of people with the IQs here. Let's go ahead and see that 26 here says between 84 and 100. Okay. Well, before we do between 84 and 100, because that's our main question here, let's at least write it down. Okay. Now, in actuality, this isn't as hard as you think, but I want you to take a look here for just a moment. Okay. Notice it says here that we have a mean of 100 and a standard deviation of 16. This is going to prove to be very important. So let's go with that idea. The mean is 100. Again, that's a random number we chose. Standard deviation is 16. All right, another random number. So the way we want to phrase this is we want to say, okay, the mean here is 100. So I'm going to write 100 down here. Let's say I made up the graph like this. I wrote it out, whatever. The mean here is 100, straight dead set in the middle. Now, if I went 1 standard deviation to the right, if I added 1 standard deviation, what score should I get over here to the right of 100? What should be my next score then? What should it be? If I take the mean and I add 1 standard deviation. So I'm taking the mean here and I'm adding, what's 1 standard deviation? So according to this problem here, what is our 1 standard deviation here? So what should I put there? Alright, I'll wait, guys. It's fine. I don't mind waiting for a while. So, I want the mean plus 1 standard deviation using the numbers that we got here. Can anybody tell me what the mean plus 1 standard deviation is going to be? How about if you add the two numbers together here, what do you get? Don't matter if you all broke. It means that, all right, good. 116. Good. Don't matter to me if you broke. I'll just wait. So, the things I'm going to stress on, this is one of them. That's correct. 116 is correct. Good. All right. What would plus 2 standard deviations be then? So let's go up again. Basically, just add another 16 to it. If you're going to go 2 standard deviations, just add another 16 to your previous result of 116. So what should you have here? Okay. All right. So I'm going to put 132. I'm going to put 132 here. Then I add another 16 to that. What do I get? All right, 48. Good. I'm going to have 148 here. Now, let's go in reverse. In this case, let's subtract 1 standard deviation. So we're going to take 100 and subtract it by 16. What do we get there? All right, we got 100 minus 16. Let's do it. Apparently this is tough, so we'll come back after 5 minutes. At least I hope not. Look, this is one of those times where I'm actually going to ask for participation because this is one of those things that you need to see like firsthand. Because then things that I'm going to talk about later won't make any sense without it. So I know I don't ask you for much, but this is one of those times where I am going to ask you guys. So because anything I do from here on out is not going to make sense. So it's kind of like you need to visualize here. 84 minus 16, what's that? We'll go to minus 2 standard deviations. What's that? 68? Good. That's minus 2 standard deviations. And let's fill in the last one here. You subtract 16 off of 68, and we're going to get 52. All right, perfect. So, as we can see here, each of these numbers here represent, again, 100 here is the mean. This part here represents subtracting off by 16 every time down to get the respective numbers here, and adding by 16 every time down to get the respective numbers here for plus standard deviations. Now, our question here is between 84 and 100. Okay. Now this is why I put these numbers in in an appropriate way, and I want to show you how we can get our answers here, because what we're trying to do here in this problem is we're trying to find out what the percentage of data items are between 84 and 100 in this normal distribution. Well, 84 is right here. Okay, this purple line we see right here, -1 standard deviation. And 100 is right smack dab in the middle. So the percentage between the purple line and the dotted line here, well, that's going to be 34%. So that's going to be straight up 34 based on what we see here. Let's try another though. Let's take a look at another here. So how about above 132? So we want to find the percentage of data items that is above 132. So what we see here is that 132 is right here. It's this line right here. Okay, the second black line you see here. And anything above 132 is going to be these two bars right here. So 2.35 and 0.15. So we add up those percentages together straight up. And so here we get 2.5%, so 2.5%. Okay. All right, now let's throw another one your way. And this time you guys tell me what it is. So let's go, sure. Let's go below 84. How about below 84? Can anybody tell me here, what percentage of the data items are going to be below 84 in this normal distribution? So I want a percentage here, okay? So that's what I want you to kind of look at here. What's the question that I'm asking you here? Notice that my answers here have been percentages, okay? 34% or 2.5%, okay? Each of these things here that are in these boxes also represent a percentage, okay? These are each percents. Okay. Again, this picture is really important, so that's why I'm kind of like a little hardcore about it. So what percentage of data items will be below a score of 84 according to what you see here on this table? %16 is correct. Nice job, Fernando. That's correct. So 84 is right here, this first purple line. And we want to look at all the percentages below that first purple line. Well, that's 13.5 plus 2.35 plus 0.15. And so indeed, that's going to be 16% at the end of the day. That's absolutely true. Okay, good. All right, so again, visualizing it and writing it out is very, very helpful. That's why I write this particular example out, because again, it's very easy to visualize what percentages you need to add using this rule appropriately. Okay. Are there any questions about that so far? All right. Okay. Let's look at the next part here then. Okay. Now the next part here is going to be also very important as well. Okay. So obviously with this rule here, obviously with this rule here has one big flaw in it. All right. While this rule can be effective, and it's very predictable and it's very effective. The issue is that you only have a limited amount of scores. Okay. So you only have +1, +2, +3 standard deviations, -1, -2, -3 standard deviations. So you have a very limited number of scores. What if you wanted to say, I want to find the data item that is, 1.73 standard deviations away from the mean, some random number like that. Well, yeah, we're going to need to know how to do that. Okay, what is going to be that what's going to necessarily be that data item there. Now we saw that example there, in the first couple of examples that we did here, but we can now talk about what's going to be called effectively. I'm going to talk about a very important topic here, which is going to be called a z-score. Okay, and so what's the definition of a z-score? A z-score here is the number of standard deviations a data item is away from the mean. Now, one thing that's important regarding a z-score is going to be this. There's two things to keep in mind. Note, there are positive and negative z-scores. Okay, so there are positive and negative z-scores. So it's possible to have a negative z-score. Again, that just represents that it is minus that many standard deviations away from the mean. So that's why I can justify saying, well, -1 standard deviation, -2 standard deviations. It means it's below the mean. It means that it's just lower, and that's okay. Okay, no problem. Okay. And the second note here to keep in mind is that every data item has a unique z-score. So you won't find two data items because of what I'm going to write down here next. You're not going to find two data items that actually are going to be actually going to have the same z-score. It's not possible. Okay, and you'll see why here in just a second, because there is a formula that goes with this. So if I want to find the z-score here, then what I do is I take the data item, I subtract it by the mean, and I divide it by the standard deviation. Okay, so again, notice I put data item minus the mean in parentheses. Okay, that's important. I want to subtract first. And then I divide by the standard deviation in order to acquire our z-score. So for example here, let's do an example. Let's say our mean here is equal to 72. And our standard deviation, I'm just making this up here, and our standard deviation is equal to 6. Okay. Okay. Let's say I wanted to find our z-score here for certain data items. Let's start off with the first data item here. Let's say the data item here is going to be, I don't know, 79. Okay, let's just go with 79. All right, so I want to find the z-score that's associated with the data item of 79. Now, I could write out the chart like I did before, but 79 may not appear on the chart because there's only a limited number of data items that you can write down. So instead, that's where we use this z-score formula here. Okay. So the z-score here, in this case, is going to equal the data item, which is 79, minus the mean, which is 72. And we'll divide that by the standard deviation, which is going to be 6. All right. And if you do this out here, do this out. 79 minus 72 will be 7. Then we take 7 divided by 6. And so 1.17, okay? Again, you can round, just to make a note here for you guys, typically rounded to 2 decimal places. This is for the homework there, just as a good side note. Again, when you try the homework there, it'll usually reference to 2 decimal places. And then, yeah, that's pretty much what they're going to ask you to do. So that's just cool. It's fine. Okay. All right. Let's have you guys give one a try. Okay. Use the mean and standard deviation that we have above. Let's try it with another data item. Let's go with the data item here of 61. All right, so let's go with the data item here of 61. Can you guys tell me what's the z-score that we get here in this case? What's the z-score that we get here in this case with a data item of 61? Let's go ahead and take a minute and give it a try. Round to two decimal places, and yeah, let's go ahead and try it. Go ahead. Once you guys, yeah, same mean. So use the same mean here and same standard deviation. So these two guys. Like I said, once you got an answer there, go ahead and put that in the chat. All right. All right, let's go ahead and give it a try. Let's go ahead and put in our z-score here of 61. That's going to be 61 for our data item minus the mean. Mean is 72. And we'll divide by the standard deviation of 6. So here we're going to do 61 minus 72. So that's going to be minus 11 over 6. So again, you can get a negative value here. So you get minus 1.83 is going to be your answer. Again, the z-score here, let's not forget, is the number of standard deviations the data item is away from the mean. So 61 here would be minus 1.83 standard deviations away from the mean. And there we go. All right. Now let's not forget here, you can also go backwards as well. So getting a data item from a z-score here. So let's say we're given a z-score. Again, we're going to use the same formula here. All right, only this time we're just going to do a little bit of trickery. So I'm just going to go ahead and put the z-score formula here. And let's do an example with this. Okay. So we're going to use a mean here. Let's change the mean here. Let's say the mean here is 50. And let's say the standard deviation here is equal to 4. Now let's go 5, actually. All right. Let's say the z-score here. Let's say the z-score here is going to equal 1.7. Again, what am I trying to find here if I have a z-score of 1.7? Well, all I'm going to do is I just want to find the data item that's associated with that particular z-score. So I'm going to set it up using my formula. 1.7 is equal to the data item minus the mean here, which is 50. I'm going to divide that by 5. Okay, next, what I'm going to do next is basically to find that data item. We're just going to use some simple algebra. All I'm going to do here is going to be, again, multiply by 5 on both sides. Okay, so on the left-hand side, I get 8.5. And that equals, again, the data item minus 50. And all we have to do is then add 50 to both sides. We're just going to add 50 to both sides just like so. And so here we get 58.5 is equal to our data item. Again, getting the data item from the z-score is really easy. Again, this also works for negative numbers. So if I would have, let's say, minus 8.5, I do 50 minus 8.5. Okay, I got a winner. All right, so it works both ways. Again, It's really not too hard to do. It's fairly straightforward. And there you go. Got it. Okay. All right. Last part here. Okay. Oh yeah, any questions by the way? No? Okay. All right. So the last thing we're going to talk about here is margin of error. All right. Now, admittingly, the margin of error that they present here in the book is not the correct way to do margin of error, but considering the resources we have, we're going to kind of have to go with this for the time being. We would actually do something slightly a bit different if it was face to face, but we're just going to kind of work with what we got here. So margin of error here can be gotten through the sample size here. So what they call it is they call it the sample size n. Like say, how many people did you ask your survey question for? Okay. All right. So basically it says there is a 95% probability, all right, that the statistic gathered lies within, and there is a formula that goes with this, so I'm going to have to type this one out. Um, wait. Oh, okay. 1 over the square root of n times 100, again, times 100%. So again, what this is really talking about here, and it's really super crude the way that the book kind of does it, to be honest, is this really strictly talks about a confidence interval. This is something that you learn in statistics here. But if you ever see a presidential poll or you see any poll of any variety, they usually have a margin of error in MOE, and they say, okay, oh yeah, this survey is like plus or minus 2.5 points or something like that. How do you acquire that? They actually go through a much deeper analysis than what the book is presenting, but that's what we call a confidence interval. You can sit there and say, okay, I know that the real support for candidate A is between this percentage and this percentage with a 95% confidence. So I'm 95% sure that it's going to be between these two percentages, and the margin of error is going to essentially tell you how far you have to go in order to get that 95% confidence. Same thing applies if you want to be like super extra sure. You're like, I want to be 99% sure. Well, if you want to be 99% sure how much support that a candidate has, for example, well then what you do is um, you're going to have to expand that interval a whole lot wider to include more possible values in order to be more sure, right? So it's just like being extra cautious. Let me expand it further so that way I know for a fact that one of those values has to be the right one. So that's one of the things that you take into account there. It's actually one of the more important things there to keep things grounded as much as possible. Because again, if you have a sample size of like 10 people, 10 people, honestly speaking, in statistics doesn't tell you anything. Okay, it really literally tells you nothing. All right, that's why when we talk about vaccine trials are tested with 30,000, 40,000 people. That tells you a whole lot more. It shows patterns. It shows consistency. Okay, that thing's very important in various studies. So if you're talking about things like margin of error, things like that, that's again one of those things that certainly does play a factor into a lot of different statistical studies. Um, really quick here, let's go ahead and show one off here. Let's say for example here, let's just do a really quick example. So this one here is honestly not a whole lot. Let's say 3,500 people watched a TV show. Okay, what is the margin of error? What is the margin of error that you can find with this sample size? So all you have to do here is just do 1 over the square root of 3,500. Okay, so times 100. So let me put it on the paint tool here. This will be 1 over the square root of 3,500. And multiply that by 100. Again, this is strictly a calculator thing. I don't expect you to do anything further than this. So here you get, 1.7%. So the margin of error, whatever that is, whatever that statistics is plus or minus 1.7%. Add or subtract it to that particular statistic. And there you go. Bada bing, bada boom. You got yourself a winner chicken dinner. Okay. All right, any questions about that? All right. No questions? All right. So that will end section 12.4 for today. Next time, we're going to go ahead and do section 12.5. And if we get through that, then we'll maybe start with section 12.6. So not a whole lot to do here. We have 2 more sections to go, and we should be good to go. I'll discuss a little bit more about the test here for next time, so that way give you a good idea about what to expect. All right? Oh man, I'm so tired right now. Okay. All right, guys. I want to thank you guys for at least sticking around here for the whole stream. I really appreciate it. All right. You guys are very nice to me. Thank you very much. I know I'm a little pushy today, but I just wanted to get some important points across. So I do apologize. I don't mean to be mean, but sometimes I just got to put my foot down a little bit and be like, "Hey, I want you to kind of understand this." So, all right. All right. Well, I want to thank you guys again. All right. I'm going to be back here at 5 o'clock, and I'm super tired. I do so badly want to talk to you, but I'm like super gone. I need to like lay down and I need to take an old man nap, Anna. So I need to do something. I'm just super old man right now. All right, guys. I'll talk to you. Yeah. I my body hates me right now. I don't know what it is. Um. All right. All right, guys. I'm gonna see you guys on Wednesday, same time, same place. All right. Have yourself a wonderful day, and we'll see you later, everybody.